Hello everyone, I want to share my recent work with Hanyu Chen, David Marsh, Eleonora Nomigender, Luca Vicinelli about the reionization in the Axiverse and the preference for low temperature reheating. I will first introduce you the axion production mechanism through freezing in the early universe and talk about the ionization history with axion decay. Then I will discuss the multi-axion decay in the string Axiverse. Finally, I will give you the conclusion. In the early universe, axion mainly freezing via the Primakoff process and the axion inverse decay through the axion photon coupling. And that two process can give us the freezing abundance. And we can calculate that from solving the Boltzmann equation. And for once we get these axions, we can study the decay influence to the ionization history. Here is the typical axion lifetime. And to study this ionization history, we can solve in this differential equation systems, which include the axion, which include the ionization rate and the baryon temperature. For the ionization equation, you can see it contains three main terms. For the first term is the standard photon ionization terms, which describe the ionization of the neutral hydrogens. And the second term is the recombination term, which describes the recombination process of the electron and the protons. And the last term is the axion decay energy deposition terms. And this second equation is about the baryon temperature. It includes the Thomson scattering and the standard cooling and the axion and the heating from the axion decay. And we have, for example, we can show this ionization history with one axion decay. The axion mass is 10 to 5 eV, and the axion photon coupling is about 10 to 6 times 10 to 13 minus 13 GeV, with the reheating temperature 5 MeV. And with that set, you can get axion abundance with 10 to minus 7, which will lead inacceptable large optical depths. And to give a new constraint on the axion decay, we have developed a new cosmological data analysis method, which is the Gaussian process regression driven the CMB data analysis. And we found that for the tau high, which is the integral through the redshift from 13 to 800, will give the most feasible constraints on this axion photon coupling parameter space. This yellow contour shows the new constraint we have, and the blue one is the previous well-known works by the Langhoff with the full treatment to the CMB data. And this red one is just the conservative assumption from which is tau low, which just goes from 13 from 0 to the 50. So once we have this consistent constraint, we can test the other properties for axions. As you can see, we can also test the maximum reheating temperature for different axion mass and coupling constants outside this colored contours. Axion space, axion parameter space can survive in higher reheating temperature until the highest reheating temperature about 10 to 16 GeV. And for the string Axiverse, it can have multi-axion decay in each models. We have tested several data sets for different Hoshi number H11. And this H11 stands for the total number of axions. And we have a series of axion models. Each model have 50 axions. And here is 2D histogram for the decay temperature and the radical density. And this decay temperature is determined by the axion mass and the coupling constants. And this different color band shows the different reheating temperature. Higher reheating temperature corresponds to the larger radical density. And also we have tested the distribution histogram for the optical depth so high with the H11 equals 50 for different possible reheating temperature. And this red dashed line shows our constraint on the optical depth. If the optical depth larger than this critical value, we can exclude these models. As you can see, when we arise this reheating temperature, more model will be excluded. And by doing so, we can test the different Hoshi numbers from 15 to 1500 or 100, 200, and 400 of 91. And we found that about 15% of axion models can be excluded at 10 to 11 GeV for this H11 equals to 50. And that ratio will decrease as we increase the reheating time, as we increase the Hoshi number. But the physics behind this result is still under study. That's the conclusion. We have got a new model-independent constraint on CMB optical depth tau high by using the GPR-driven CMB data analysis, which can nearly consistent with full-power CMB analysis. Thus, we can do a feasible and a faithfully test to the Axiverse with many axion decay. And we found that 50% of these models in the H11 equals 15 ensemble prefer low reheating temperature, about 10 to 11 or 10 to 13 GeV at 60 at 16.8 or the 95% confidence level. And we found that the fraction of excluded geometry decreased as the Hoshi number increased. and the physical reason for this result is still under consideration. So we will update soon when the work shown on arXiv. Thank you.